Welcome everybody. This would be a lecture on weight update rules for neural networks, various possible schemes in this course on intelligent control. We have already discussed various feed-forward neural networks, multi-layered neural networks, radial basis function neural network, and associated algorithms for these networks. Also, we proposed in the last class a very interesting algorithm for weight update, that was the adaptive learning rate using Lyapunov function. So, we will now summarize the various schemes that are being employed to improve on the convergence property as well as the global convergence criteria for minimizing a cost function given a network. So, it would be a kind of a summary to let you know what is the state of art of various weight update rules for specifically feed forward networks. So, topics that would be covered today would be conventional training algorithm, gradient descent that we have already been talking about, which is popularly known as back propagation algorithm for feed forward networks, Newton's method, quasi-Newton method, conjugate gradient method, and these methods would be kind of compared with our schemes also that we proposed last time. That is our personal work, the work of our group at IIT Kanpur on adaptive learning rate, and then we would kind of summarize everything that we have learned. So, introduction. Feed forward neural networks are used as function approximators for learning mappings between input and output space, right. A neural network is represented as y equal to f w x, that is, if I have a neural network here, this is some neural network, then my output vector, okay, is y and input vector is x. Neural network is characterized by weight vector w. Then my output of neural network is a nonlinear function of weight vector w and input x. Weight vector w is updated in such a way that a specific cost function is minimized such that network can predict for the test data. So, we give some data, we generate some training examples for this network for training, and then with another set of such examples we test the predictability of this network. Desirable features of learning algorithm: locating global minimum of the cost function, first convergence, good generalization, that is learning from minimum examples. So, I take minimum examples and then this network learns network is provided with minimum example, and from that example it can if the network can extract the map of the entire data that is there in input output space for that specific domain, and the prediction is pretty nice. So, then that is a good generalization. Less computational complexity. So, this is very important, we do not want to have an algorithm that takes a long time for computation, so very fast, like back propagation algorithm with all its drawbacks is very fast. It is simply a first order approximation of Taylor series approximation, the back propagation that tries to minimize. So, it is very fast, this algorithm is. So, the traditionally that people have tried to propose various algorithms for feed forward neural networks, including the even feedback neural networks that we have already talked. All these things can be applied both to feedback and feed forward network for system identification, because we are talking about intelligent control. So, when we talk about neural network, we are talking in terms of either system identification or control. So, all these gradient descent, Newton's method, quasi-Newton method, conjugate gradient method, all these methods, the variant of these methods have been applied to neural network to varying degree of success. So, cost function, normally a cost function is a function of a weight. You see that this is so while training a neural network, the cost function is usually written as this, where this is your desired output, this is your actual output predicted by the neural network, and then for P is the stands for pattern. So, if I have n patterns, so this total error, square of the error should be minimized. This is not the normally this is a quadratic cost function, but not necessarily we go for this function, but usually researchers they use this kind of function, this function, this type of function. And here if you look at what is YP, this YP is the output of the neural network, and YP is function of neural network weight, and XP is the neural network input. Okay. So, this XP is input, YP is output, and so in that sense you can easily see that E is actually a function of W, because since Y, P, D and XP are known. Given a training example, given a training set, then I know what is YPD. In YP also this function I know what is XP. So, all that I do not know is the weight vector. So, in that sense my cost function is simply a function of weight vector. Thus, E is a nonlinear function of weight vector W, and it will be represented as EW. You understand why we are writing EW, means E is a function of exclusively a function of W when we train a neural network. The objective of learning is to find W star such that EW star is optimized or minimized. Usually we minimize the error. So, recursive form of a general learning algorithm is weight vector new is equal to weight vector old plus delta W with an initial condition W naught. Okay, we start with some initial condition. So, now let us talk about gradient descent. I mean, what we are trying to do in this lecture is that I would like to give you a comprehensive picture of all this learning algorithm that we are being talking about until now. So, let us talk about a gradient descent algorithm. What is actually a gradient descent? What it does? We understood in our previous discussion, it certainly does not take us to, or it does not guarantee us to global convergence, or theoretically the gradient descent cannot take us to a gradient descent, to the global minimum. Okay. So, that is, if we have a cost function like this E and this is W. So, obviously, if I start from here I may reach here, if I start from here then I may reach here. So, it all depends on the initial condition where I am starting, and since I do not know where is the global minimum, so how can I fix a initial condition that will be very near to the global minimum. So, it is very difficult, no theoretically gradient descent cannot ensure global convergence, it only ensures local convergence. So, in that sense what gradient descent does? Let us think about the function that we talked about, that we are trying to minimize, EW, error function. So, if I expand this error function around W naught, okay, some initial point, okay. So, and I do a Taylor series expansion, then you see that EW naught plus delta E by del W delta W first order, second order term, that is del square E by del W square delta W square, this is whole square actually, and plus so on. So, this is the series what we are talking about, and if we neglect in this expansion second order and higher order terms, that is, if I simply consider the first order Taylor series expansion of the cost function, then this is my expression. Okay. So, the approximation first order of this is first order approximation of EW. Okay. First order Taylor series expansion, TS. TS is Taylor series. So this is this is what we have written here, Taylor series. So this Taylor series expansion of the cost function, the first order Taylor series, looks like this particular which is given in this block. Now, if I select delta W as minus eta del E upon del W transpose, right. You know that E is a scalar. When I differentiate a scalar with respect to a vector, it becomes a row vector. So, transpose makes it a column vector, and delta W is a column vector. Okay. So, we get if I replace this delta W, this particular expression in the previous expression, and that expression is that we wrote earlier, E hat is E W naught plus del E upon del W in delta W. So, in this, replace this delta W by this minus eta del E upon del W transpose. So, if you do that, then E minus EW will become this quantity, because if you take this one here, so you get minus eta del E upon del W norm square, and since this is a norm quantity which is always a positive quantity, so hence this this particular term is always negative. What it implies? It implies that if I start from W naught, the next W, the update, would be always less than EW naught. Okay. So, that is, again, when this W will become the initial point and you go to the next point, so it will always decrease. This would always decrease, because the it will always decrease. In which sense? The decrease is ensured only when in terms of the when EW is looked at as a first order approximation of Taylor series. Okay. But this is not always, if this is not true, I can't say EW is less than equal to EW naught. This is E hat W, and E hat W is a first order Taylor series approximation of the cost function. So, the gradient descent algorithm ensures that the first order approximation E hat W reaches its global minimum, but it does not ensure global convergence for the original cost function EW. So, in that sense, what gradient descent does, it tries to optimize the first order Taylor series expansion of first order Taylor series approximation of the original cost function. So, in that sense we only reach a local convergence. So, the gradient descent algorithm as usual is given by this. So, learning rate eta determines the speed of convergence. Convergence depends on proper choice of initial conditions, that I have already told you. So, now let us take a simple example of a gradient descent. EW is 0.5 W square minus 8 sin W plus 7. So, this is a nonlinear cost function. So, it is a multimodal function with 2 local minima and a global minimum. The gradient descent update law for parameter W is obtained as this. Okay. So, delta W is minus eta del E by del W. So, if I differentiate this, I get eta, this is 2 into 0.5 1. So, W minus 8 cos W, and this is 0. So, that you see that this particular cost function, this is actually EW. So, this EW it has 2 local minimum and 1 global minimum. So, interestingly, if you look at the result is, if I use adaptive value eta equal to 0.01, which you are seeing, that is a red one, circle one. So, if I start from this point, okay, W naught is minus 8, if I start from there. So, what I am seeing that this comes and slowly converges at this point and does not go from there. So, it actually converges to local minimum. So, if I start from here, I reach here, but if I change eta equal to from 0.01 to eta equal to 0.4, if I take, then my eta's step size, learning rate size has increased a little bit. So, you can easily see that this square one. So, from this point it jumps to this point, and from this point it goes to this point, and again from here until it converges to global minimum in this case. Okay. So, changing this eta, I am able to again reach in this case to the global minimum. So, when eta is 0.01, W naught is minus 8, the final weight W equal to minus 4 corresponds to local minimum. Okay. This one minus 4. When eta equal to 0.4 and W naught is minus 8, the local minimum can be avoided, and final weight ultimately settles down at global minimum, okay, at this point. So, I reach the global minimum, but this is a simple function, and because this is a simple function, we are able to show that by changing this eta intelligently we can reach it. Okay. But if the function is complex, we have no idea, we have no comprehensive method to reach the global minimum using gradient descent. Although heuristically we can reach, like near global minimum. So, observation: for small step size, gradient descent gets stuck at local minimum. For larger step size, it may come out of local minima and get into global minima. Algorithm may not converge for larger step size as well. There is no comprehensive method to select initial weight W naught and the learning rate eta for a given problem, so that the global convergence is achieved. Okay. So that the global convergence is achieved. Okay. So, that is about gradient descent. Now, because gradient descent is very slow in its convergence, it does not guarantee global convergence. So, people thought about Newton's algorithm, where like in gradient descent the weight update law is such that it tries to find the global minimum of the first order Taylor series approximation of the cost function. Now, in Newton algorithm if we take the same cost function EW and again we expand its Taylor series and we take the second order approximation here. Okay. So, if we take a second order approximation, so and here let us define G as del E upon del W, the gradient vector, and there is a Hessian matrix that is defined as H, which is dou square E upon dou W transpose. So, neglecting higher order terms, we have following second order approximation of the cost function. So, this is the second order approximation. Here EW is the second order Taylor series approximation of actual cost function EW, okay, and that we write in this particular form. Okay. So, the all other higher order terms from this point onwards has been neglected. So, this is a quadratic function of delta W. The necessary condition for minimization of E hat W, which is a second order approximation of actual cost function, is given by del E upon del W is 0, which gives the following update law for weight vector, which delta W is H inverse G. Okay. So, that is, if I go here and if I differentiate this del E W by del W, okay, this is a constant term, goes away. So, differentiating this, I get delta W is H inverse G, H inverse G. Okay, this is my weight update law. Using Newton's logarithm. But unfortunately, of course, now once I take this, you can easily see that E hat minus E W naught is always a negative definite quantity, provided, not always, it is negative definite only when H is positive definite. Okay. So, this is true provided H is positive definite, means H is positive definite. I hope all of you understand positive definite weight. If I take any vector x transpose H x, okay, if H is a positive definite matrix, this quantity is always a positive quantity for any except any null vector. You take any vector x, this will be a positive quantity. So, that is H is positive definite. So, in that from that sense, that this algorithm is not a foolproof algorithm, because even it does not guarantee locally stable unless H is positive definite. That is the biggest drawback of a Newton algorithm, but still researchers have used it because it is very fast. But you see that it requires, this weight update algorithm requires H inverse of a Hessian matrix. Imagine a normal network has at least hundreds of weights. So, W the minimal order is 100. So, H has at least 100 by 100, the dimension of H would be at least 100 by 100. I said not 100 by 100 because it is a double derivative. So, it is a huge, the dimension is huge and inversion is computationally very expensive. So, in that sense, this algorithm, although we can use this algorithm to solve a simple cost function optimization, but in terms of a neural network, this is I would say it is an infeasible algorithm. We can't implement it because Hessian cannot be computed. It will take a lot of time. So, the Newton algorithm, starting with any initial condition W naught, iterate following equation until stopping criteria is met, which is W t plus 1 is W t minus H inverse G t. This is the Newton algorithm, and the discussion is that the Hessian matrix S t has to be positive definite matrix for all t. That has to be, we can't guarantee H all the time. Stepen descent method operates on the basis of a linear approximation of the cost function, while Newton's method uses quadratic approximation of the error surface around the current point W t. Computationally intensive as it requires matrix inversion H inverse. For non-quadratic cost function E w, convergence is not guaranteed. This makes it unsuitable for training feed-forward network. Now, we will take the same example that we considered earlier. E w is a scalar. You see that w is a scalar. It's not, w is not a vector here, simply a scalar. So, it is a very simple function, 0.5 w square minus 8 sin w plus 7, and if I use the and because w is a scalar, naturally del E upon del w is a scalar, which is g, and H is del E by del square E by del w square. So, that is also a scalar, and if and weight update law delta w is minus eta H inverse. So, H here is a scalar, so it is inverse into G, that is our algorithm, where G w is f dash w. See, this is not f, this is E dash w, this is E double dash, that is this dash represent, this is actually del E by del w, and this is del square E by del w square. Okay. So, this is this represent this, and this represent this, and using this, if you update, you see that for some initial condition, when w naught is minus 6, eta is 0.01, the weight diverges, that is because H is not positive definite. So, in this case H is not positive definite. Okay. So, H is a scalar here, as obviously it is not greater than 0, it is a negative quantity, and when w naught is minus 7 and eta is 0.001, the final weight converges to local minimum here, and when w naught equal to 0. So, this from, if you start from here you reach here, but if you start from here you reach here. Okay. The final weight converges to the global minimum, but then we really did not achieve much with respect to in comparison to gradient descent, except probably the gradient descent even converging to the local minimum, whatever the number of steps it will take to go to the local minimum, probably using this Newton method you can improve on that speed, but no way the desired goal of learning is achieved by Newton method. So, observations are as follows: convergence to global minimum depends on the selection of proper initial condition w naught. Algorithm may diverge for unsuitable initial condition because H w is not a positive quantity, or in fact in general I would not say H is a scalar for our example, but in general H, the Hessian matrix, is not positive definite, okay, or is not positive definite always.